In 1809, German botanist H.F. Link was the first to record the observations of the Myxobacteria, identifying its fruiting bodies as a gastromycete. The fruiting bodies that Link witnessed was later found to be one of the most remarkable aspects of myxobacterial distinct social behavior. However, only since the beginning of the 1980s have the Myxobacteria become a fascinating object of microbiological research. The Myxobacteria are gram-negative unicellular rod-shaped bacteria that are commonly found in soil. Taxonomically, Myxobacteria are considered an order called Myxococcales. Sampling sites of the Myxobacteria have been found around the world. The Myxobacteria are ubiquitous and are generally found to be mesophiles. However, the entirety distribution ecology still remains in question due to the fact that so many of the Myxobacteria remain uncultivated. Here, Myxococcus xanthus, the most highly studied myxobacterium, preys on E. coli cells and moves and feeds cooperatively as a predatory group, creating a multicellular structure called a swarm. When the swarm make contact with the E. coli prey, thousands of cells eventually penetrate the prey colony and lyse the cells via the secretion of secondary metabolites. Then, the Myxobacteria digest the prey extracellularly into smaller compounds that it can uptake as nutrients. Myxobacteria swarm over prey cells in rippling swarms that degenerate into mounds as nutrients become scarce. As the cell density within the mounds increases, the cells aggregate to form macrostructures called fruiting bodies, shown here, inside which a small proportion of cells develop into spores. The fruiting body structures are so large they are visible to the naked eye. They are shown here on WCX minimal media stained in blue banded dye. Here, vegetative cells from Chondromyces apiculatus, freshly germinated from two different fruiting bodies, form two distinct swarms on a solid agar surface. Myxobacterial motility is distinct in that it involves cell-to-cell interactions as opposed to individual movement via, say, a flagella. Although individual cell movement is faster, Myxobacteria opt to move collectively, gliding at about 10 to 60 micrometers per minute on average. When Myxobacteria swarm and eventually lyse prey, they create what are called secondary metabolites. Secondary metabolites are compounds not directly involved in the normal growth, development, and reproduction of an organism, but are rather primarily involved in the overall maintenance and homeostasis of the organism. Secondary metabolites are natural products that can be used to create novel antibiotics. Myxobacteria are prophyllic producers of secondary metabolites. These secondary metabolites are unique and diverse and can be used to create novel antibiotic, anti-cancer, and antiviral drugs. In the last 6 years alone, 42 new secondary metabolites have been described from members of the Myxobacteria, several of which are being tested in preclinical studies. For example, Syrangium cellulosum has been found to produce a clinical anti-tumor compound called ipothalone. In the time of growth of pan-resistant pathogens and antibiotic resistance, the number of new classes antibiotics has only stagnated. Myxobacteria are a potential source of novel antibiotics, but a majority of them remain uncultivated, as shown in this phylogenetic tree constructed from 16S ribosomal RNA surveys. The red represents Myxobacteria that are cultivated, and the black represents Myxobacteria that are uncultivated. With the exception of the suborder Myxococcus and the Cystobacteriaceae suborder, the phylogenetic tree remains untouched in terms of cultivation. In order to increase our chances in finding novel secondary metabolites that can be used to make antibiotics, we have to explore all areas of Myxobacteria phylogenetic tree. In summary, Myxobacteria are a group of predatory soil bacteria that can be characterized by their ability to produce bioactive secondary metabolites that can be used to create novel drugs. In order to really gauge the potential of Myxobacteria, we need to further tap into their phylogenetic diversity.